Good evening, everyone. Good evening, good evening, good evening. Good evening, everyone. Good evening. I welcome you all again to the JEE Enthuse. Hi, Kirito. Hi, Saima. Hi, Catalysis Fan Club. Hi, Tanu. How are you guys doing? I'm doing wonderful. I'm doing wonderful, Kirito. How are you? Hi, Sai Karthik. Good evening. Good evening. I'm doing wonderful. I'm doing wonderful. How are you doing? Yes. How are you guys doing? Thank you, Tanupriya. Thank you. Thank you. That's wonderful, Kirito. Hi, Navneet. How are you? IOQM and JEE 2023. Hi. Hello. What's up? Hi, Tawkir. Hi, cool girl. Good evening. Wonderful, guys. Great, great. So, as you all must be knowing, in the last session, we talked about the reversible and the irreversible processes. And in the today's session, we are going to talk about the isothermal processes in detail. Yes, today we are going to talk about the isothermal process in detail, right? That is wonderful. You're from Jammu. That's wonderful. That's great. Catalysis Fan Club is saying Josh is full. That's actually wonderful. That's great. Okay. All right. All right, guys. So before starting the session, as you all know, my name is Wassim Sir and I'm your chemistry master teacher over here, right? So people, let me show you the schedule of the week first, which I show in every session, as you all must be knowing now. In the last session, we talked about the reversible and the irreversible processes. Today, we are going to talk about the isothermal process. Tomorrow, we are going to talk about the adiabatic processes. On Thursday, we'll talk about the polytropic processes. On Friday, we'll be talking about free expansion and the cyclic processes. And on the Saturday, we'll be talking about the entropy of the system surrounding and the universe. Yes, on Saturday, we'll be talking about the entropy. Talking about the Menti quiz, guys. Let me show you the schedule of the Menti quiz as well. On every Tuesday, you have got the Menti quiz with the Shimon Sir. On Thursdays, you have got the Menti quiz with the Shreya Sir. And on Saturday, you have got Menti quiz with me at 1 p.m. on electrochemistry. Yes, that is great. That is great. So, guys, do not forget to add in this session, okay? So before starting, do like, share and subscribe to the channel so that everyone will get benefited out of these sessions, as I always say in the every session, okay? So people, for the Vedantu JEE Pro subscription, what all benefits you guys are going to get if you'll enroll yourself in these Pro subscriptions? I need to give you the brief description of that. You guys are going to get the 5,000 plus hours of live online teaching. Regular tests and assignments will be provided to you, which contains more than 10,000 questions. We have got 20 plus teachers with 5+ years of experience who will be constantly helping you out, personally training you for the upcoming JEE 2021 and JEE 2022, okay? And you have got the option to learn either in English or in Hindi. The choice is completely yours to select the language, yes? And at the end, let me tell you, we are going to cover everything over here, which includes your micro as well as the crash course. Yes? For the ones who are going to appear in the JEE in 2021, we have come up with 3 different plans for you: 1 month plan, 3 month plan and 6 month plan. And these are the rates of these plans after the 20% off. It's completely your wish to select the plan, okay? If you're taking 1 month plan after the 20% off, you're just getting it for 6K, okay? 3 month plan 16.8, 6 month plan 31.2 and so on. Yes. Hi VSG, good evening, good evening. Hi Ashwarya, good evening. Nishant, you're my long-term batch student. That's wonderful. Hi Rishabh, good evening. Okay, for the ones who are going to appear in the JEE in 2022, we have come up with 4 different plans for you, okay? And in all these 4 different plans, you have got 20% off. And after the 20% off, you are getting the plans over here. You can have a look on their actual rates after the 20% off, yeah? Okay, for the droppers, there are 3 plans: 1 month, 3 month and 6 month plan. 1 month plan after the 20% off, you guys are getting it for 7.2K. And 3 month plan after the 20% off, you guys are getting it for 20.4. And the 6 month plan after the 20% off, you guys are getting it for 40.8K. Now the point is how to get enrolled in these Pro subscription, how to take any of the plan. There's a link in the description box, guys. Just click on that link in the description box of the video. Okay, use the coupon code as WBPRO. You guys are going to get the 20% off in whatever. You guys are going to get the 20% off in whatever plan you're choosing for yourself. Yes, now need as sprints can be part of it. Yes, absolutely. Okay. For for NEET crash course, I mean for NEET subscriptions, for NEET plans, you can go to the NEET Lead channel where I take chemistry. You can check the video. In the starting of every video, I tell about the NEET Pro subscriptions as well. So go to the NEET Elite channel, check it there, right? Yes, VSG, it's going to be another amazing session. Yes, absolutely. Anisha, I'm doing wonderful. Hi, Fahim, how are you? Okay. All right. So people, are you super excited for the session? Let me know in the chat box first, then only I'll be starting the session. Let me know in the chat box if you guys are super duper excited for the session. Yes. Let me know in the chat box if you guys are super duper excited for today's session. Because today you guys are going to learn a lot of new things. Trust me on that. Yeah. A lot of new things you guys are going to get. So let's kill this topic, isothermal process. Let's understand what this isothermal process is all about. Guys, can you get anything from this diagram? Can you get anything from this GIF? Yeah? See guys, volume of the gas is increasing, but the temperature is not changing. Temperature is not changing as I'm continuously giving heat to the system. So can I conclude one thing? Can I say whenever there will be isothermal expansion, heat is absorbed by the system? Yes. Anyways, we are going to talk about this in detail, okay? Have a look, guys. Okay, so let's talk about the isothermal processes. Let's talk about the isothermal processes. Understand properly what I'm going to say, okay? See, guys. For example, this is the container which I have. And in this container, I have got an ideal gas. Let's say this is the ideal gas which I have in the container. Correct? Let's say the piston is right now at point A and volume occupied by this ideal gas right now is V1. The pressure of this ideal gas right now is P1. Number of moles of gas present in this container right now is N. The temperature of this ideal gas right now is T. Yes, this is something which I have. I've got the gas, ideal gas in the container, which is my system. Okay, when the piston is at point A, volume occupied by the gas is V1, its pressure is P1, its temperature is T, its moles are N, right? Now people, for example, I need to do the expansion of the gas. For example, I need to do the expansion of the gas. Yes. For example, I have to take this piston from point A to point B. Let's say when the piston reaches at point B, the pressure of the gas when the piston reaches at point B becomes P2. Volume of the gas when the piston reaches at point B is V2. Let's say number of moles of the gas are still N. Let's say temperature of the system, temperature of the gas is still T. So first of all, what am I doing? Can I simply say over here V2 is greater than V1, final volume of the gas is greater than initial volume because I'm doing the expansion? Yes. And people, during this expansion, if the temperature of the gas is kept fixed, for example, I'm not letting the temperature of the gas to change. I'm keeping the temperature of the gas as constant. I'll be calling this expansion as the isothermal expansion. Yes. So what is isothermal expansion right here? Whenever there is expansion during which temperature of the gas does not change, okay, during this expansion, if the temperature of the gas is not changing, I'll be calling this expansion as the isothermal expansion. If the temperature of the gas is kept fixed, if the temperature of the gas is kept constant. Yes. Similarly, talking about isothermal compression, correct? Let's say this is the initial position of piston, and in this container, I've got the ideal gas, right? Let's say the temperature of the ideal gas right now is T. Yes. Now I want this piston to come inwards and I want this piston to stop here somewhere at point B. Correct? During this process, can I first of all say when the piston will be coming inwards, volume of the container will be decreasing. So I'll be calling this process compression. Yes. And during this process, if the temperature of the gas is not changing, during this process, if the temperature of the gas is maintained constant, okay, I'll be calling this process as isothermal compression then. Yes. So isothermal process in general, which can be either isothermal expansion or isothermal compression. Yes. During any expansion or compression, if the temperature of the ideal gas is kept fixed, is kept constant, we call that process as the isothermal process. Very, very, very simple. Yeah. Now people, let's try to understand this in detail. See guys, first of all, in case of isothermal process, what we got to know, temperature of the gas, temperature of the system is kept fixed, is kept constant. Yes. Now people, at the same time, if the temperature of the gas, or I would say temperature of the system is kept constant, can I say delta T value is 0? Yes. Now if the delta T is 0, can I say delta U value for the ideal gas which is in the container, right? That will be also 0. Yes, definitely. Definitely guys, very, very simple. If for any process, first of all, my system is my ideal gas, right? I've taken an ideal gas present in the container, correct? If the ideal gas, which is my system right now, if it is undergoing the isothermal process, either isothermal expansion or isothermal compression, I would say temperature of that ideal gas will be kept constant. Delta T value for that ideal gas will be 0. Delta U value for that ideal gas will be 0 because delta U is equal to NCV delta T. Since delta T is 0, so delta U is 0. Yes, number one. Number two, guys, if I'll use the first law of thermodynamics, delta U is equal to Q plus W. Delta U is equal to Q plus W. For isothermal process, we got to know delta U is 0. If delta U is 0, I would say for isothermal process, Q will be equal to minus W, right? This is the relation which your isothermal process will follow. Yes, this is valid for the isothermal process. Now people, two things can happen. Either isothermal expansion will be happening or isothermal compression will be happening. Yes, either isothermal expansion will be happening or isothermal compression will be happening, right? Now guys, first thing, if the value of W for the system, if the value of W, in general I'm saying, if the value of W is coming as negative, let's say the value of W is coming as negative, right? If the values of W is coming as negative, what does that mean? That means I'm talking about expansion. That means I'm talking about expansion. If the value of W will be coming as positive, that means I'm talking about compression, right? If the value of W will be positive. Yes. Now people, if the value of W comes out to be negative, if the value of W comes out to be negative, negative becomes positive, so Q value comes out to be positive. And when can the Q value come as positive? When heat is absorbed by the system. When heat is absorbed by the system. When heat is absorbed by the system. I'll make you understand its actual feel in some time, okay? Let's try to understand this mathematically first, then we'll get to know about it properly, okay? Similarly, guys, if there be compression, W value is going to be positive. If W value is positive, then Q value will be negative. Q value will be negative. People, if Q value will be negative, I will say heat will be released by the system. I would say heat is released by the system. Heat is released by the system. Now guys, let's try to analyze these statements properly. I can say during isothermal expansion, during isothermal expansion of an ideal gas, heat is absorbed by the system. First statement which you got. Similarly, during isothermal compression, heat is released by the system. Yes, I'm going to write these two things in the statement form, then I'll make you understand what it actually means, okay? So mathematically we got to know whenever there will be expansion of the ideal gas happening isothermally, heat will be constantly absorbed by the system. Whenever there will be isothermal compression of the ideal gas, heat will be released by the system. Now how can we get the real feel of it? That I'll be telling you in after 2 minutes. But before that, I just need to write these two things in the form of a statement so that you are never going to forget these things, okay? I'm writing during isothermal expansion, of an ideal gas, heat is absorbed by the system. Heat is absorbed by the system. This is the first statement which we got. First, let's try to visualize this statement. Let's try to understand this statement. Yes, let's try to understand this statement. See, what as per this statement, we saw mathematically during isothermal expansion of an ideal gas, heat is absorbed by the system. Why it happens? Understand that as well. See, See guys, this is the container which I have. Understand properly, right? This is the container which I have, and in this container I have got the gas. I've got the gas. Let's say volume of the gas right now is V1. Let's say temperature of the gas right now is T1. Correct? Now people, if I'll ask you, on this piston, how many pressures will be acting? One is going to be your pressure of gas. One is going to be your external pressure. I need to show you the expansion. I need to show you the expansion. That means P gas must be greater than P external. Then only the piston has to come out. Then only piston will be coming out. Initially, the piston was at point A. If P gas is greater than P external, then only piston will come out and will reach point B. When the piston reaches at point B, volume of the container increased. Okay, and if the volume of the container is increasing, I would say volume of the gas is increasing from V1 to V2. Correct? But I have to still maintain the temperature at T. During this expansion, the temperature of the system, the temperature of the gas should not change. Now, how is that possible? How is that possible? We need to think about it. See, first of all, when the piston will be going from A to B, can I say this is the case of expansion, and whenever there is expansion, work is done by the system. So when the piston is moving from A to B, work is done by the gas against this external pressure. Work is done by the gas against this external pressure. Now people, if gas is doing work, when the piston is moving from A to B, gas is doing work. That means gas will be consuming its internal energy to do this work. Yes, in order to perform work, gas will be consuming its own internal energy. Then only it will be performing this work against this external pressure. So during this expansion, gas is performing work. Gas is doing work. Gas is consuming its own internal energy in order to perform this work against this external pressure. Now people, what is going to happen to the internal energy of the gas with time? Can I say internal energy of the gas with time will decrease? And remember, internal energy is directly proportional to temperature. So when the piston will be moving from A to B, the gas is doing work against external pressure. Internal energy of the gas will be decreasing. If the internal energy of the gas will be decreasing, temperature of the gas will decrease also. But do I have to let the temperature of the gas to change? No. How temperature will remain maintained? How temperature will maintain? When I'll supply heat to the system. Yes. If I'm not going to supply heat to the system, then the temperature of the gas will decrease because the internal energy of the gas is decreasing when the piston is moving from A to B. Yes. Yes, but I do not have to let the temperature of the gas to decrease. That is why I'm giving energy continuously in the form of heat so that temperature remains the same. Yes. So remember, during isothermal expansion of the ideal gas, heat is absorbed by the system in order to keep the temperature same. Let me know in the chat box if it's clear. Let me know in the chat box if it's clear, guys, so that I can talk about one more important statement. Yes. Kirito is saying it's epic, huh? That's wonderful, Kirito. Wonderful, guys. I'm writing one more statement which we got to know mathematically a few minutes back. Now, hi Abdullah, welcome. Welcome, bro, you are late. Now, people, one more statement. During isothermal compression, of an ideal gas, heat is released by the system. Heat is released by the system, which we saw mathematically. Now let's try to visualize it. During isothermal compression of the ideal gas, heat is released by the system. How can we understand this? See, guys, this is the container right here, and this is the piston. Okay, we have got the ideal gas in the container. For example, if the piston has to finally reach at point B, let's say the piston has to finally reach at point B. Yes, the piston has to finally reach at point B. Initially, the piston was at point A. Finally, piston has to reach at point B. So is this the case of expansion of compression? This is the case of compression. During this compression, I have to keep the temperature of the system fixed. I do not have to let the temperature of the system to change. I do not have to let the temperature of the system to change. I have to keep the temperature of the system as fixed. How will I do that? How will I do that? How will I do that? Now guys, see what is going to happen. Whenever piston will be moving from A to B, whenever piston will be moving from A to B, this is the case of compression. Whenever there is compression, work is done on the gas, work is done on the system. Whatever work is done right now during this process, when the piston is moving from A to B, work is done on the gas because it's a case of compression. Whatever work is done on the gas, that work is getting stored in the gas in the form of internal energy. When the piston moves from A to B, this is the case of compression. This is the case of compression. Work is done on the gas, and whatever work is done on the gas, that work is getting stored in the gas in the form of its internal energy. So can I say when the piston is moving from A to B, internal energy of the gas is getting increased with time when the piston moves from A to B? Because when the piston moves from A to B, work is done on the gas, and that work which is done on the gas, that is getting stored in the form of internal energy. That is getting stored by the gas in the form of internal energy. Yes? Yes? That is getting stored in the form of internal energy. So with time, when the piston moves from A to B, I would say internal energy of the gas will increase. Yes? If the internal energy of the gas will increase, can I say temperature of the gas will increase? But do I have to let the temperature of the gas to increase or decrease? No. Since the piston is moving from A to B, work is done on the gas. Whatever work is done on the gas, that work is getting stored by the gas in the form of its internal energy. So whenever piston moves from A to B, internal energy of the gas will keep on increasing. So temperature of the gas will keep on increasing. But do I have to let the temperature of the gas to increase? No. For that, what should happen? The gas should continuously release heat so that temperature of the system remains fixed, so that temperature of the gas does not change. Yes? Yes? Very, very, very simple. So that's what I've written over here. During isothermal compression of an ideal gas, heat is released by the system. Yes? Got it? Got it? Let me know in the chat box if you got it. Fast. Let me know in the chat box. Yes, Abdullah, you can tell me what is it? Yes, Karthik, you're right. No issues, Abdullah. It's okay. It's okay. Matthew, the conventions in physics and chemistry, it's opposite. Okay. Let's move on, guys. Let's move on and talk about a few more important things. This is something which I've told you. During isothermal expansion, heat is absorbed by the system. During isothermal compression, heat is released by the system. This is something which we have discussed. Yes? Done. Yes? Yes, Nifa, you can join. Okay, one more thing, guys. For the isothermal process, or let me write it for you. For the ideal gas undergoing the isothermal process, delta U as well as delta H for it will be 0. Yes, because we know delta U is equal to NCV delta T and delta H is equal to NCP delta T. For isothermal process, temperature is constant, delta T is 0. So this value is 0, this value is 0 for the ideal gas which will be undergoing the isothermal process. Remember this, at the same time we have discussed this as well. Yes? We have discussed it as well, if you remember. Okay, now people, how do we calculate work done in reversible isothermal process? How do we calculate work done in reversible isothermal process? Okay, understand, guys. For example, I have to do the expansion of 5 liters. Okay, let's say I have to do 5 liter expansion of an ideal gas. Yes, I have to do the expansion of 5 liters for an ideal gas. And I have to do this expansion isothermally. The temperature of the gas should not change. The temperature of the gas should not change while doing the expansion of 5 liters. Now I have got two options. Either I can do this isothermal expansion reversibly, or I will do the isothermal expansion irreversibly. How do we calculate work done in reversible isothermal process? How do we calculate work done in irreversible isothermal process? One thing I told you in last session, in reversible processes, how do we calculate work? If you remember in the last session, I told you integral from V1 to V2, P gas, pressure of gas multiplied by dV. This is how we calculate work done in reversible process. And in case of irreversible process, external pressure is constant, so it becomes minus P external delta V. Very simple. This is something which we have discussed in the last session. Yes, this is how we calculate work done in irreversible process. This is how do we calculate work done in reversible process. Yes, as you all must be knowing. Abhishek in chemistry, yes. Hi Aditya, hi, welcome bro. KK, it's in chemistry, absolutely. Now guys, see, now the point is how do we calculate the work done in a reversible isothermal process? How do we calculate it exactly? First of all, in all the reversible processes, how do we calculate work? Work in reversible process, simple, minus integral from V1 to V2. This is P gas multiplied by dV. If you remember the same expression we have discussed in the last session. Yes. Now guys, understand. Let's say this is the container which I have, and the piston is right now at point A, and in this container we have got the ideal gas. Let's say I've got n moles of ideal gas. Yes, I've got n moles of ideal gas. The volume of the gas right now is V1, the pressure of the gas right now is P1, okay, and the temperature of the gas right now is T, right? Now people, I have to do the expansion. I have to take this piston out from A to B. Correct? I'm doing the expansion. When I took the piston from A to B, let's say volume of the gas is V2, pressure of the gas is P2, temperature still is T, number of moles still are N. Okay? So should I be calling this expansion when the piston is moving from A to B? Should I be calling this as isothermal expansion? Definitely I'm doing it isothermally during this process. When the piston moves from A to B, I'm not letting the temperature of the gas to change. Yes, I'm not letting the temperature of the gas to change. Now I've got two options. Either I'll be doing this expansion fastly or I'll be doing this expansion slowly. When I'll do this expansion slowly, I'll be calling it as a reversible isothermal expansion. Now people, how do we calculate work done in case of reversible isothermal process? Okay, how do we calculate work done in any reversible isothermal process? It can be reversible isothermal expansion or it can be reversible isothermal compression. How do we calculate work? That is the point. Yes. See, I've got the ideal gas in the container. Yes, I've got the ideal gas. If there is an ideal gas in the container, can I say ideal gas should follow this equation PV is equal to nRT? Yes, where P is the pressure of the gas. Can I say pressure of the gas will be equal to nRT divided by V? Absolutely. Pressure of the gas will be simply nRT divided by V. Correct? Now people, I can write it like this. W reversible. Work done in reversible isothermal process will be integral from V1 to V2. P gas, I can simply write from the ideal gas equation as nRT divided by V multiplied by dV. I can do that. So work done in reversible isothermal process will be integral. I'll take nRT out. So this will be integral of dV by V, which is going to be ln of V. Give the upper limit, give the lower limit. This is going to be ln of V2 divided by V1. Or you can write it like this. Work done in reversible isothermal process will be equal to minus 2.303 nRT. This is going to be log of V2 divided by V1 to the base 10. Yes, this is something which I'll remember from now onwards in order to calculate the work done in isothermal reversible processes. Yes, absolutely. Yeah. Now people, one more thing. Since the gas in the container is your ideal gas, right? And the ideal gas is kept at constant temperature. Yes, ideal gas is kept at constant temperature, correct? I mean, during this process, during this expansion, I'm not letting the temperature of the gas to change. So should this ideal gas follow the Boyle's law? Definitely it should follow the Boyle's law. And as per Boyle's law, you all must be knowing P1 V1 is equal to P2 V2. Yes. Can I write P1 divided by P2 is equal to V2 divided by V1? Yes. So instead of this V2 by V1, you can write P1 by P2 as well. The choice is completely yours. So you got one more equation. To calculate the work done in reversible isothermal process. In case of reversible isothermal process, it's going to be minus 2.303. I'll write nRT. I'll write log to the base 10. Then it becomes P1 divided by P2. This is one more relation which I can use in order to calculate the work done in reversible isothermal process. Now you have to look into the question whether you are given with the pressure data or you are given with the volume data. If you are given with the volume data, you'll be using this relation. If you are given with the pressure data, you'll be using this relation. Yes? Very simple. Yes, absolutely. Yes, Kirito. Now guys, see, this was how to calculate work done in reversible isothermal process. Now the point is, how do we calculate work done in irreversible isothermal process? In irreversible isothermal process, how do we calculate work? In all the irreversible processes, we calculate work like this: minus P external V2 minus V1, since external pressure is constant in all the irreversible processes. Yes? Yes? Holy Bible, this is very, very important. This is the most important chapter as far as your JEE is concerned, the thermodynamics. Yes? Now. See, this is the formula by means of which we calculate work done in irreversible isothermal, in any irreversible process. Yes? Right now we are talking about the irreversible isothermal process. So I'll be using the same formula. Or people, I can do like this. The gas, initially, its pressure was P1, its volume was V1, its temperature was T1. Its temperature was T. Let's keep it as T, correct? Now finally, the pressure of the gas was P2, the volume of the gas was V2, but temperature was still T, right? I'm not letting the temperature of the gas to change, right? I'm not letting the temperature of the gas to change, correct? Number of moles of the gas are also fixed, are also constant. I'm not letting the number of moles of the gas to change as well, okay? So people, I can modify this equation. I can write W irreversible will be equal to minus P external. Instead of V2, can I write it like this? nRT divided by P2 from ideal gas equation minus nRT divided by P1 from ideal gas equation. If I'll take nRT common on both the sides, I'll get one more expression in order to calculate work done in isothermal irreversible process, and it's going to be minus P external. This is going to be nRT. This is going to be 1 divided by P2 minus 1 divided by P1. So I have two expressions by means of which we can calculate work done in irreversible isothermal process. Yes, these are the two expressions by means of which we can calculate the work done in irreversible isothermal process. I'm sure this is clear. Yes? Yes? Let's Saurav, what's up? Okay, wonderful guys. So I'm going to talk about one more important thing, okay, which is really, really very important, okay, and you need to understand that properly. Okay. These are the two statements which you need to understand. These are really, really, really important, okay. First thing we got to know till now. During isothermal expansion of the ideal gas, heat is absorbed by the system. Heat is absorbed by the gas, right? Heat is absorbed by the gas. During isothermal compression of the ideal gas, heat is released by the gas. These things we got to know till now, yes? During isothermal expansion, heat is absorbed by the gas. During isothermal compression, heat is released by the gas. All these things we got to know. Now. If you look at the first statement, guys, I want you guys to have a look on the first statement, then I'll make you understand what this statement is all about. For the same amount of expansion, heat absorbed by the system in reversible isothermal expansion is more than that of in irreversible isothermal expansion. Okay, what does that mean? Now that looks interesting, yeah? For the same amount of compression, heat absorbed by the system in reversible isothermal compression is more than that of irreversible isothermal compression is more than that of reversible isothermal compression. What does that mean? Let's try to understand these. Yes, let's Saurav, P2 will be always equal to external pressure. Yes. Absolutely. Final pressure external pressure के बराबर होगा. I'll show you that in the problems. Just wait for some time. Yes. Let's try to visualize these two statements first. Let's try to understand these two statements first. But before doing these statements, we should know first of all, whenever there is isothermal expansion, heat is absorbed by the gas. Yes, we got to know that. Before some time we got to know whenever there is isothermal expansion, heat is absorbed by the gas. Whenever there is isothermal compression, heat is released by the gas. Yes, we got to know that. Yes. Now. The statement is almost done. See guys, see. First of all, I can do the isothermal expansion. Let's say I have to do the isothermal expansion of 5 liters. Let's say I have to do the expansion of 5 liters isothermally. I can do this expansion by 2 ways. Either I'll do this isothermal expansion either I'll do it reversibly, or I can do it irreversibly. Yes. See, I have to do the isothermal expansion of 5 liters. Yes. I can do it reversibly or irreversibly. Choice is all mine. Yes. Now during isothermal expansion, heat is absorbed by the gas. Now, among these two cases, where will be the heat absorbed by the gas more? Where gas is going to absorb more heat? We have to check that. Yes. Do you remember I told you in the last session, magnitude of work in reversible expansion is greater than magnitude of work in irreversible expansion? Yes. Do you remember that? I told you in the last session. I gave you the proof of it as well. Magnitude of work in reversible expansion is always greater than magnitude of work in irreversible expansion. Do you remember? So can I say over here gas is going to do more work? Gas is going to do more work, right? Because I'm talking about expansion. Work is done by the gas, and reversibly, I would say gas is going to do more work. If gas is going to do more work, that means gas is consuming its internal energy more. If the gas is consuming its internal energy more, I would say the final internal energy of the gas will be the minimum in case of reversible process. If the final internal energy of the gas is minimum, can I say its temperature will decrease the minimum? Its temperature will decrease the maximum. If its temperature will decrease the maximum, do I have to let the temperature to change? No. That means I have to supply more amount of heat here. I'm not sure whether you got it or not. Yes? Yes? Once more I'm going to tell you. See, understand properly. I have to do the expansion of 5 liters, correct? I have to do the isothermal expansion of 5 liters. Now I can do the isothermal expansion of 5 liters reversibly or irreversibly, correct? During expansion, work is done by the gas. In this reversible expansion as well as irreversible expansion, work is done by the gas. But over here, work is done more by the gas. In case of reversible, magnitude of work in case of reversible expansion is more than that of magnitude of work in irreversible expansion. Yes? Now I can say over here in reversible isothermal expansion, work done by the gas will be more. If work done by the gas will be more, I would say gas has consumed its more internal energy over here. If the gas has consumed its more internal energy, that means its temperature will be decreasing fastly. Yes? Or I will say it like this. I'll say it like this. See, work done by the gas over here is more. So the gas has utilized its internal energy more over here. If the gas has utilized its internal energy more over here, final temperature of the gas will be minimum over here as compared to this. If the final temperature of the gas is minimum over here as compared to this one, I would say I have to supply more heat. Such that the temperature remains the constant. Yes. So can I simply say heat absorbed by the system in case of reversible isothermal expansion will be always greater than heat absorbed by the system in case of irreversible isothermal expansion? Do you know that? Did you get it? Yes? Let me know in the chat box fast if it's clear. Simple guys, over here gas is doing more work. Gas is utilizing more internal energy. If gas is utilizing more internal energy, in order to keep the temperature fixed, I need to supply more heat energy such that the temperature remains the same, such that the temperature does not change. So I would say heat absorbed by the system in reversible isothermal expansion is always greater than heat absorbed by the system in irreversible isothermal expansion. People, let me know in the chat box if this statement is clear to you. Yes. Yes. Hi, Nikhil. Wonderful, guys. Great. Okay. Okay. This was about expansion process, right? Talking about compression. What do you think? What do you think, guys? What do you think? See, for example, I have to do the isothermal compression of 5 liters. Let's say I have to do the isothermal compression of 5 liters. Now, I can do this isothermal compression in 2 ways. I can do this isothermal compression in 2 ways. Just a second. I can do this isothermal compression of 5 liters in 2 ways. Either I'll be doing it reversibly or I'll be doing it irreversibly. Do you remember in the last session I told you magnitude of work in irreversible compression, magnitude of work in irreversible compression is greater than magnitude of work in reversible compression? Yes. And we know during compression, what happens? During isothermal compression, heat is released by the gas. We talked about that before some time. During isothermal compression, heat is released by the gas. Now I need to check in both the ones. Where will be the heat released more? Where will be the heat released more? Can you tell me that? Where will be the heat released more? Can you tell me that? Can you tell me that? I'm waiting for your answers. Tell me fast. Tell me fast. Can you tell me where will be the heat released more? Let me know fast in the chat box. What do you think? See, first of all, I'm right now doing the isothermal compression. If I'm doing the isothermal compression, heat will be released, right? Now, in which case heat released will be more, in reversible or irreversible? What do you think? Simple. Magnitude of work in irreversible compression is greater than magnitude of work in reversible compression. Yes. 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 Now understand it properly. The way I think, you think the same. See, if magnitude of work in irreversible compression is more, during compression work is done on the gas. Now more work is done on the gas in irreversible compression. If more work is done on the gas in irreversible compression, more internal energy is more energy is getting stored in the form of internal energy during irreversible compression. You're getting it? Yes. So more heat energy needs to get released in order to maintain the temperature. Yes? Understand it like this. Understand it like this. See, again I'm telling the same thing. Again I'm telling the same thing. See, magnitude of work in irreversible compression is more. So more work is done on the gas during irreversible compression. If more work is done on the gas, more energy is getting stored in the gas in the form of internal energy in this irreversible compression. If more energy is stored in the gas in the form of internal energy, can I say more energy needs to get released over here so that the temperature remains the same? Yes? Yes? So can I simply say heat released? Can I simply say magnitude of heat released by the system in irreversible compression will be greater than heat released by the system in reversible compression? Let me know in the chat box if this statement is clear to you. Again, one more important statement. Yes? Yes? Arsalan, you can just replay the video a bit. Just take the video, थोड़ा पीछे ले लो video को, खुद ब खुद repeat हो जाएगा. Yes? Very, very, very simple. Yeah? So people, that is why I had given these two statements. Just a second. I had given these two statements. Where are those? Just a second. For the same amount of expansion, heat absorbed by the system in reversible isothermal expansion is more than that of irreversible isothermal expansion. For the same amount of compression, heat released by the system in irreversible isothermal compression is more than that of reversible isothermal compression. Yes? So remember this. Remember this. Absolutely, Navneet. Absolutely, absolutely. You're absolutely correct. You're absolutely correct. Okay. Now, guys, we have got the first question on the screen. The first question on the screen. Let's try to understand this question. Let's try to solve this. Okay. See, 2 liters of N2 gas we have got 2 liters of N2 gas, right? Initial volume of N2 gas is 2 liters, correct? At 0 degrees centigrade. Temperature of this O2 gas is 0 degrees centigrade. And 5 atm. Pressure of this O2 gas right now is 5 atm. Initial conditions. Are exploded isothermally. Isothermal process happening against a constant external pressure. Against a constant external pressure. That means it is the irreversible isothermal process. Against the external constant pressure. That means it's the irreversible isothermal process. Yes. So I got to know it is irreversible isothermal process. Irreversible isothermal process. Against the constant external pressure of 1 atm. So external pressure is also given to me as 1 atm. Yes. Until the pressure of the gas reaches 1 atm. So final pressure of the gas P2 is equal to how much? It is 1 atm. Yes. How much heat will be absorbed or released? How much heat will be absorbed or released? First of all, initial pressure of the gas is 5 atm. Final pressure of the gas is 1 atm. And it is the isothermal process. Temperature is constant. Yes. At constant temperature for the ideal gas, pressure is inversely proportional to volume. Is the pressure of the gas increasing or decreasing? Pressure of the gas is decreasing. If the pressure is decreasing, volume is increasing. That means this is the case of isothermal expansion. During isothermal expansion, heat is absorbed by the gas. So over here, heat will be first of all absorbed by the gas. So this one is correct. Heat will be absorbed by the gas because we know during isothermal expansion, heat is absorbed by the gas. Very simple. Now, how much heat is absorbed by the gas? That we have to check. First of all, everything's happening at isothermally. I mean, everything is happening isothermal. Temperature is kept constant. Yes. At constant temperature, do you know P1 V1 is equal to P2 V2? Yes. P1 is the initial pressure of the gas, V1 is initial volume, P2 is final volume, P2 is final pressure, V2 is final volume. Yes. What is the value of P1? Initial pressure of gas, that is 5 atm. What is the value of initial volume of gas? That is 2 liters. P2, final pressure, that is 1 multiplied by V2. So I would say final volume of the gas is 10 liters, right? This is the final volume of the gas, 10 liters, expansion. Initially the volume was 2 liters, finally the volume reached to 10 liters. Yes, I can see that. Now people, this is the case of irreversible isothermal expansion. How do we calculate work done in irreversible isothermal processes? It is simply equal to minus P external V2 minus V1. Yes. Guys, tell me, are we given with the value of P external? P external pressure is given to me as 1 atm. V2 is 10, V1 is 2, 10 minus 2 is 8. So the value is coming as minus 8 atm liter. This is the value of work, right? Now use the first law of thermodynamics, as you all must be knowing. For the isothermal process, delta U is 0, so Q is equal to minus W. If Q is equal to minus W, that means Q will be equal to plus 8 atm liter. Plus 8 atm liter, right? This much heat will be absorbed by the gas. Right? This much heat will be absorbed by the gas during this expansion. You can see the value of Q is coming out to be positive. Yes? Very simple. Now people, you can convert it into joules as well, as I have already given you the conversion. 1 atm liter is equal to 101.3 joules. Yes? So I can say 8 multiplied by 101.3 joules. This much heat will be absorbed by the gas during this expansion. Let me know in the chat box if it's clear fast. Let me know in the chat box if it's clear fast. Let me know in the chat box if it's clear fast. Exactly, Navneet. This is work of expansion. Yes, absolutely. Yes. Wonderful. I'm moving on to one more question then. Let me see if you can solve this or not. Again, a very, very simple question. Calculate Q, W, delta U and delta H in calories when 2 moles of ideal gas, N value is 2 first of all, N value is 2, correct? When 2 moles of an ideal gas are expanded reversibly and isothermally. So process is reversible isothermal. Process is reversible isothermal and the gas is expanded. So reversible isothermal expansion. This is something which is given to me, right? From 10 atm to 5 atm, right? So initial pressure of the gas is 10 atm. Final pressure of the gas is how much? It is 5 atm. Yes, it is 5 atm at 27 degrees centigrade. Temperature is 27 degrees centigrade. That means 300 Kelvin. Assume Ln2 is 0. We have to calculate Q, W, delta U, delta H. First thing, since the process is isothermal, and for isothermal processes, for the ideal gas, delta U and delta H are always equal to 0 if you remember. Because delta U is equal to NCV delta T, delta H is equal to NCP delta T. First thing, delta U and delta H for the isothermal process it's 0. Absolutely, Kirito, you are right. Yes, Abdullah, absolutely. Now. Now, what are we supposed to calculate? We are supposed to calculate W and Q. Since the process is reversible, for reversible process, how do we calculate? For reversible isothermal process, how do we calculate work? I've already given you one expression. What was that? I guess that was minus nRT ln V2 by V1 or P1 by P2. This was one expression which I gave to you. Yes? Do you remember this? The question is done. N value is given to me. That is 2. R value. Since I have to calculate delta, all these values in calories. So I'll be using the value of R as 2 calories per Kelvin per mole. Yes, temperature is given to me as 300 Kelvin. Ln of P1 by P2. P1 is 10, P2 is 5. 10 by 5 is 2. So ln of 2. Ln of 2 value is given in the equation itself. That is 0.7. We have to take it as 0.7. So it will be minus 2 2s are 4 multiplied by 300 multiplied by 0.7. So what will be the value coming? Tell me guys fast. Tell me guys fast. What is the value exactly coming? What is the value exactly coming? It will be minus 1200 into 0.7. So it's going to be minus 960. Yes, it is going to be minus 960 calories. This is the value of work. This is the value of work, right? You can get it easily. W value is coming as negative. That means expansion is happening, which we already know. Pressure is decreasing. That means volume is increasing. Yes. If W value you got as minus 90, we know for isothermal process Q is equal to minus W. So Q you will be getting as 960 calories. So this much of heat will be absorbed by the system during this expansion. Sign is coming as positive. Yes? 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 Kirito, it is given in the equation, expanded reversibly and isothermally. It is given in the equation, it's reversible. Or if in a question it's mentioned that expansion is happening against constant pressure, against constant external pressure itself, means that the process is irreversible. Yeah? Yes? Okay. Oh, this coming as minus 840. Okay, this coming as minus 840. Just my bad. Minus 840. Done? Yes? Okay. I'm moving on to one more question. Let me see if you can solve this or not. This is the question. This is the question. And you guys are going to do it. This is your homework. This is your homework. Okay? This is your homework. I want all of you to give it a try and let me know the answer in the comment box afterwards. Okay? There's one thing which you need to understand in the question. There is one thing which you need to understand in the question. 6 moles of an ideal gas expands isothermally from 1 liter to 10 liter. Gas is getting expanded isothermally from 1 liter to 10 liter at 300 Kelvin. Calculate maximum work done by the gas. Now, it's not mentioned whether the process is reversible or irreversible. You need to use your brains. Calculate the maximum work done by the gas. Can you tell me what you will do in this question? Can you tell me which formula will we use in this question? Should I be considering it as reversible or irreversible? Can you tell me that first? Just tell me that first. We are supposed to calculate the maximum work done by the gas. Should I be considering it as reversible or irreversible? As it's not mentioned in the question, right? Tell me. Should we be considering it reversible or irreversible? It's very simple, guys. Since we are supposed to calculate the maximum work, and you already know magnitude of work in reversible expansion is always greater than magnitude of work in irreversible expansion. So work can be only maximum if the process will be happening reversibly. So I'll be using the reversible value formula right here and get the answer. Yeah? Yes? And let me know the answer in the comment box afterwards. Yeah? Do let me know the answer. Okay? So people, this was all for today. Okay? I'm sure your isothermal concept is clear. I'm sure you remember everything now. Let me summarize everything first. First, in the beginning, we talked about the reversible. I showed you what is reversible isothermal process. Yes? Okay. Okay, if you remember, in the beginning itself, I told you what are isothermal processes in which temperature is kept constant. Delta T will be 0. For an ideal gas undergoing isothermal process, delta U as well as delta H will be 0. Yes. And after that, what did we talk about? I showed you during isothermal expansion, heat is absorbed by the system. During isothermal compression, heat is released by the system. Then I told you during reversible isothermal expansion, heat absorbed by the system is more as compared to irreversible isothermal expansion. And after that, I talked about during irreversible isothermal compression, heat released by the system is more as compared to reversible isothermal compression. Yes. Then I gave you two formulas to calculate work done in reversible isothermal and irreversible isothermal process. Yes. And I told you at the end, whenever in a question you will see a statement written that the expansion is happening against constant external pressure, that actually means the process irreversible. Yeah. Very, very simple. And at the same time, we know magnitude of work in reversible expansion is always greater than magnitude of work in irreversible expansion. Yes. Thank you, Matthew. Thank you. Thank you. Thank you. Okay. So people, talking about one more thing, that is JEE 2021 crash course, which we are starting on the long term, in the actual Vedantu platform. So what I want you guys to do, if you are actually planning to crack your JEE 2021, you should enroll yourself, because we are going to train you personally in this crash course, right? In your physics, chemistry, as well as mathematics, right? Okay, so do get enrolled in this, right? And you are going to get all the benefits. You are going to get the personal attention of the teachers. That is the best part over here, right? Okay, and how do we enroll ourselves in this crash course? There is a link in the description box. Click on that link regarding the crash course. Use the coupon code as WSCC. You'll be getting the 20% off in this as well. People, don't forget to get added in the Telegram group as well, because in the Telegram group, you stay updated about the classes and the important information regarding the classes. Yes? Okay, and at the end, do like, share and subscribe to the channel so that everyone will get benefited out of it. People, I'll see you guys tomorrow at 5:30, and tomorrow, let me tell you, we are going to talk about even more important process. That's what we call as adiabatic process, okay? In the tomorrow session, I'm going to classify your adiabatic process into reversible adiabatic, irreversible adiabatic. I'm going to show you how to calculate the final temperature in reversible and irreversible, which is the scoring topic from your JEE point of view, right? So I'll see you guys tomorrow at 5:30. Till then, you guys take care. Bye-bye. God bless you all and love you all. Take care, guys. Take care.